My dear student, colleagues, and all the viewers watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good afternoon to all. So, hope you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, and situation becoming worse day by day. So, we have to follow our health rule. It's very difficult for us to continue our normal academic program inside the campus. We have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started this online program, including online international physics webinar. We have successfully completed our 221 international physics webinar. Today it's our 222nd. And today we'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics, Indian Institute of Technology, Gandhinagar. And we have with us here today Dr. Prasanna Venkatesh, Assistant Professor, Department of Physics, Indian Institute of Technology, Gandhinagar. And he has already connected with us. So Dr. Prasanna, welcome to our webinar, and thanks for accepting our invitation. So before going to you, I'd like to introduce you with our student and the viewers. So dear student and viewers, I think you have already come to know the title of this today's International Physics webinar. Title is an invitation to ultra-cold atom in a cavity via Bloch oscillation. And our speaker is Dr. Prasanna Venkatesh, Assistant Professor, Department of Physics, Indian Institute of Technology, IIT, Gandhinagar, India. And our speaker, Dr. Prasanna, has completed his bachelor degree from Chennai Mathematical Institute and his master's and PhD degree from McMaster University. Then he did his postdoc from the Asia Pacific Center for Theoretical Physics, South Korea, and then he did his another postdoc from Institute of Quantum Optics and Quantum Information, Austria. His research interest is area of quantum optics, ultra-cold atomic physics, and quantum thermodynamics. So I think you will enjoy this session, and you can also ask question by commenting, and you will also join with us by using this link. So thanks for your patience. I think you will enjoy our session. So Dr. Prasanna, it's your time. You can start your session.
Yeah. Okay.
And
Thanks a lot. Yeah. Thanks a lot, Pretam. I hope you can see my screen. I'm making it full screen. And so, okay. All right. Thanks a lot for that very nice introduction. And I'm really glad that I'm able to join you all for this talk. So as Pretam mentioned, the title of my talk is An Invitation to Ultracold Atoms in a Cavity via Bloch Oscillations. So my main sort of motivation today is to introduce this field of ultracold atoms in a cavity as pedagogically as possible, because I was informed there are more undergraduate students in the population. So I would say that I'll try and keep it, the pedagogical part, the longer one. And then if time permits, I'll get to a point where I might discuss a research work that I've been sort of involved in since my PhD times, and regarding Bloch oscillations of atoms in a cavity, as in one example of what you can do with ultracold atoms in a cavity as a broad field. Okay, so that's the sort of overall introduction. And so let me begin with a slightly more detailed introduction as to what this entire thing is about. So let's start even more basic. So the field that I'm working in is this quantum optics. And the main sort of one of the big goals of quantum optics is to identify, control, and use quantum degrees of freedom in nature. Okay, so why do you want to do this? There are, let's say, let me just give you a couple of examples of why this is very useful and interesting if we are able to do this. The first big example is that if you're able to identify, control, and use quantum degrees of freedom, I can build up from sort of ab initio very interesting quantum systems that are controllable, and I can use them to simulate other hard to simulate quantum systems. I'll come back to this idea. This is called quantum simulation. And this is a great way to, because as of now, very complex quantum systems cannot be simulated on classical computers. That is one direction why this goal is very interesting, or one of the benefits we get by going along this goal. The second thing that can happen is if we are able to do this, we can actually make quantum computers. The reason that we have working small-scale quantum computers now is because we were able to identify, control, and use degrees of freedom, quantum degrees of freedom. Okay, so that's the whole goal of quantum optics. Before I proceed to the next slide of my introduction, I just wanted to say that I'll stop, let's say, every 10-15 minutes and or let's say 15 to 20 minutes, and then I'll ask Pretam if there are questions so that it doesn't become a one-way thing. So okay, so that's the goal of quantum optics. Okay, then let's one way to enable this quantum control is, or the one way to enable this ability to control quantum systems very well. So this idea of quantum control within quantum optics, if we want to do this, how do we do it? The best idea is there are only two objects in quantum optics. That is the main objects in quantum optics. We have atoms and we have light. So the study of atoms and light is quantum optics. And if you want to control either light better with atoms or atoms better with light, you have to make them talk to each other very well. Okay. But I want to first emphasize to you that this is not an easy task. In order to do that, consider the simplest sort of model of an atom. So a two-level system with some excited state and ground state. These are electronic orbitals of a single electron of an atom, bound electron, let's say. And then these atoms will have, basically these two levels will have a particular quantized separation of energies, which is the resonance frequency of the atom omega 0 or omega A, as I'll call it. And it also has associated to that frequency, that transition, there is a wavelength that is given by lambda 0. Now let's ask, what is the probability that if I impinge on this atom with basically a focused laser beam, what is the probability that the atom can scatter light from that laser beam? Okay. One way to estimate this probability of scattering is to consider the area of cross-section, scattering cross-section of a single atom when it is illuminated with light that is resonant with the optical transition. This area, there is only one length scale in the problem, the wavelength, it has to just be proportional to the lambda 0 squared. That if we divide that by the effective area of the laser beam, so the cross-sectional area of this laser beam, right? This A effective, then that will give us the probability that we get scattering of light by a single atom, right? Now we want this probability to be as large as possible to do better and better quantum control, right? Now there is a fundamental issue here. Now if you take a laser with photons of wavelength lambda 0, you know that there is something called the diffraction limit. I cannot focus a laser beam to much below lambda 0. Basically, I can only focus, the smallest area that I can focus to is of the order of lambda 0 squared. So this A effective is at best lambda 0 squared. So once you plug that in, so this A effective is always greater than lambda 0 squared. It will be actually many factors times lambda 0 squared. One immediately reaches a problem. The probability of scattering of a single photon from a laser beam by a single atom is really tiny. So the entire sort of motivation of the things that I'm going to talk about is to consider strategies where you make this scattering probability larger and larger. Okay, so that's the main idea. I'm going to present two strategies to do this. The first strategy is, instead of a single atom, somehow you manage to put many atoms together and make the laser beam interact with this. In this case, you get an enhancement of the scattering given by the number of atoms or the ensemble number that interacts with the light. Okay, so that's one strategy. The second strategy is a little bit more nuanced and interesting. What do? Instead of just applying a laser beam in free space, you actually put two mirrors, which is basically a cavity, and you send in laser light from outside the mirror inside. So then inside this cavity, if you make mirrors which are very, very shiny and that can reflect light very well, a single photon basically bounces many, many, many times. Each time it has some probability to escape, but the probability to escape is set by how shiny or how reflective the mirror is. But you can make really nice mirrors, and that is possible now with technology. And as a result, you can basically enhance this scattering probability by the number of bounces that the photon makes before leaving the cavity. So this probability of scattering in the cavity QED scenario, which is what QED means, quantum electrodynamics, cavity light in atom light interaction, that's what I'm going to call as cavity QED. It's like a field. So now in this limit, one gets an enhancement. In this strategy, one gets an enhancement of the scattering probability purely from the number of bounces of the photon. So then these are two very complementary and interesting strategies which allow atoms and light to talk better. In a sense, the kind of things I'm going to talk about is going to take advantage of both these strategies, which is, in one strategy, I want to find a way to get many atoms together, trapped, such that they can interact with light. And in the second strategy, I want light to bounce between two mirrors many times and interact strongly with each atom. So a mixture of these two strategies is what I'm going to talk about, and this is the field of ultracold atoms inside cavities. Okay. So now I'm going to actually be very pedagogical and mathematical about how to write down the basic physics of cavity QED, almost a tutorial way, I hope. But before that, I want to give you a taste for what sort of cool things can one do with cavity QED. And I'm going to do that as always in this field. There are much more beautiful experiments than, let's say, theory. In some sense, theory and experiments go very hand in hand. So when you want to convey the excitement of this field, you always have multiple experiments that you can choose. I'm just going to choose two very important experiments and just give you an idea of what sort of great things one can do with cavity QED. So the first example of I want to take is a very now almost 20 years old experiment from the lab of Jeff Kimball in Caltech. What they did there was they had a cavity. So this is basically at the these are sort of mirrors, and this is basically the gap between the mirrors, which is what the cavity is. And above these mirrors, they had a cloud of trapped, very cold cesium atoms, and the atoms, they can in a controllable manner allow the atoms to fall one by one through the cavity. As the atoms fall through the cavity, they have a probe laser that illuminates the cavity, and they can read out the transmitted light coming from the cavity. Now, the beautiful thing is that as the atoms interact with the light in the cavity, as soon as an atom enters the cavity, you can very easily sense that there is a single atom that is entering. And as soon as that detection is done, they basically crank up the intensity of the laser field. And as a result, they basically trap this single atom in a cavity. And this figure here is a beautiful example of basically the light that they see. As soon as they see a cavity, as soon as they see an atom, they crank up the light field. So then as soon as that happens and single atom is trapped, and from this light signal that they get out, they can really reconstruct the motion of a single atom inside a cavity. So that is the first sort of major thing. Imagine this is really a single atom. It's almost impossible to overemphasize how hard this is, because an atom is such a small object, but you can really study the motion of a single atom in space using this cavity. So this is one big advantage of cavities, where I can use a cavity to probe the dynamics of atoms inside it. Okay. The second big, I want to then look at the second experiment. This is from the lab of Serge Haroche in France. And here you studied an atom using light. Now the roles are reversed in this experiment by Haroche, where they take Rydberg atoms, which are basically very large dipole atoms. So they're atoms with very large dipole moments. They're put into states which have very large dipole moments, and they are passed one by one through a superconducting cavity. All right. And before they are passed into you can again think of them as large dipoles, but still this will be like a two-level system. There is an excited and a ground state. They initially prepare this atom in a superposition of excited and ground state, and then they run it through the cavity. So the cavity's photon, the light field photon frequency, is not the same as the atom's separation frequency. As a result, it only shifts the phase of this superposition. Okay, so if you send in E plus G, it will shift it to E plus some E to the I phi times G. So it will basically rotate. If you know the Bloch sphere or the qubit, it rotates the qubit in the equatorial plane. And the amount by which it rotates, the phase shift, the amount of the phase shift is controlled by the number of photons in the cavity. Okay. As a result, as soon as the atoms exist, they can do a post-processing and immediately find out what is the number of photons in the cavity. Okay. And now what they did was they cooled this cavity down to very low temperatures, so much so that there is at best 0 or 1 photon in the cavity. And then as they passed atoms one by one, they can very beautifully see, as shown here, these are basically streams of atoms that are passing through the cavity, and they are detected later. If the atom is in the excited state, then if the atom is detected in the excited state, the experiment is arranged such that if I see an atom in the excited state, then I know that the cavity has 1 photon. If I see the atom in the ground state, the cavity has 0 photons. And one can beautifully see that as the atoms pass through, the cavity is in a quantum state. It's actually a thermal state at some very low temperature. So 0 or 1 photons are maximally occupied. And one can see very nicely that as the atoms pass through one by one into the cavity, sometimes you actually find a single photon in the cavity. So this is like you see the birth of a single photon, and suddenly that single photon leaves the cavity. And then so the cavity has no photons. So this is a very beautiful experiment showing the high degree of control we have in cavity QED and in quantum optics in general. And of course, this was rightly awarded with the Nobel Prize for Serge Haroche, and also to David Weinman, who did experiments which are sort of the inverse of this strategy. So now I've talked about strategy 1, cavity QED, and I just want to then talk to you a little bit about the second strategy, which is ultracold atoms and Bose-Einstein condensation, where this second strategy, remember, is to get many atoms together and trap them, and basically also bring them to really cold temperatures so that quantum mechanics becomes important. So in this process, you end up producing a very interesting state of matter called the Bose-Einstein condensate. But before that, I just want to specify the big milestones in this second strategy, which is first they had to find a way to really cool atoms to very low temperatures. So this technology, which is called laser cooling, where you can use lasers to slow down fast-moving atoms and hence get a large number of atoms in a small region at low temperatures. This was pioneered by many people. Some of them were awarded with a Nobel Prize: Stephen Chu, Claude Cohen-Tanorji, and Bill Phillips. I saw that Bill Phillips had given a talk in this seminar also, which is very great. And also there was seminal work by Arthur Ashkin, who was later awarded a Nobel for related work, but even his contribution to getting laser cooling going was immense. And so now they can even make very beautiful atomic traps, and which can actually be put into space, right? So people are trying to actually make very cold atoms and put them in space and test them in microgravity and so on. But so that's the first thing they had to do. Then as you keep going to even lower and lower temperatures, this collection of atoms below a certain critical temperature goes into this very fascinating quantum state, which is called the Bose-Einstein condensate, right? Named after, S.N. Bose. And this state is very interesting. And what all that I could go on and discuss this in more details, but for our sort of simple picture, what you can think of this as basically below this Bose-Einstein condensate temperature, where you take a collection of atoms and go really cold, basically the atoms lose all their individual identity and become what is called a matter wave. Okay, so this is very nice because you can basically put 1 million atoms, when you make this kind of a Bose-Einstein condensate, into a single quantum wave function. And this allows basically, and this was awarded again with a Nobel Prize in 2001. And this making of this Bose-Einstein condensate really set in motion this idea of quantum simulation I want to describe to you. Basically, now with this Bose-Einstein condensate, we have essentially highly controllable quantum state of many atoms. Okay, so then what good is it for? It's very interesting because these are atoms. You can always apply laser light, and not only can you apply laser light, but you can apply periodic laser light, which means you can actually apply lasers in 3 directions and create a periodic potential for the atoms. Such a laser light induced potential for atoms is called an optical lattice. And as soon as people were able to realize this, they recognized a pioneering idea that Feynman had and decided to use this idea to study ultracold atoms. Now, what was this idea? This idea was very beautiful. Basically, once you have a very large collection of single quantum particles and you look at how do you simulate the behavior of this collection, you quickly realize that unlike classical particles, because of the structure of quantum mechanics and quantum mechanical states, the computational power you require blows up. If you know quantum mechanics, the size of the Hilbert space, so to speak, just blows up. So no classical computer can, for example, simulate 20 electrons in a solid. You can write down all the Hamiltonian, everything very easily. It is just Coulomb interactions, ion Coulomb interaction. Everything is easy to write down the Hamiltonian, but it is impossible to exactly simulate. So Feynman came up with this idea that, well, and the other interesting and hard problem is that these systems are also hard to manipulate and experimentally study as well. Now, Feynman said that, if you have some very interesting properties of a complicated quantum mechanical system, which you cannot simulate with a regular classical computer, why not make an analogous quantum system, which you can control very well, and implement the same physics in this hard to control quantum system, and hence study what sort of physics will come in this hard to control system using an analog quantum system. So this is the idea of quantum simulation. And a big example of this quantum simulation was realized when they this was realized in the group of Immanuel Bloch in Munich in 2002, where they, after making a Bose-Einstein condensate, they put this Bose-Einstein condensate in an optical lattice potential, pictured here as basically like an egg crate. Now, when the optical lattice is very low depth, when the lattice potential is, the barriers between the wells of this crate are very small, the atoms continue to be in this Bose-Einstein condensed phase, and they also move about freely without dissipation, which means they are called a superfluid. And as a result, they are essentially able to hold on to their matter wave property, which is the Bose-Einstein condensate property, very well. And all that the lattice does is it basically causes a diffraction of this matter wave. And this is basically the momentum distribution of the atom, which reveals the diffraction pattern due to the lattice. Okay, but now as you keep increasing the strength of this lattice potential, eventually the atoms go into a completely different quantum mechanical state from the Bose-Einstein condensate. This state, which is a strongly correlated quantum state, is called a Mott insulator, and the atoms cannot freely tunnel between the wells of this lattice anymore, and they occupy each, there is some finite occupation of each of the wells, and as a result, this is no longer a coherent matter wave, and there is basically no matter wave diffraction pattern that you can study. Okay, and this transition was mapped out and studied using this ultracold atomic system in this experiment. And now, meanwhile, the technology has gone even better, where you can actually take pictures of this optical lattice really, and single atoms in this optical lattice. These are pictures of a Mott insulator. For example, here is a picture of a Mott insulator. This last picture, when the lattice depth is very large, showing that atoms are really occupying every lattice site, whereas if the lattice depth is very small, the atoms are distributed amongst different sites and they can freely tunnel. So this was done by a method called quantum gas microscopy, which is the current state of the art to study such many body physics. And what is amazing is this is like the theorist's dream in some sense, where you can make a complicated quantum many body state, but you can study it 1 degree of freedom at a time, which is impossible to imagine in any condensed matter system, solid state system. And that is the whole dream of quantum simulation, and we've achieved quite a few things with this. Okay, so now I just wanted to end my introduction by saying that we have talked about two strategies. We can put single atoms into cavities and study them with high quantum degree of control, and we can make really cold gases of atoms, possibly in a Bose-Einstein condensed state. And both of these methods have different advantages. In one case, you can study the system in novel ways. The light and the atom can interact strongly. In the second case, you can put the atoms into coherent matter wave states, like the Bose-Einstein condensate. And what happens when you combine the two by basically putting an Bose-Einstein condensate inside a cavity, as has been done by an experiment in Esslinger's lab in Zurich, or you can even put cold atoms into a cavity, as was done in another experiment that is schematically shown. So which is basically you have cold atoms put into this cavity, which is shown in this picture schematically. And this is the cavity in the same way that I showed. Two mirrors, and you make a Bose-Einstein condensate outside and you can bring them in. Now, what sort of phenomena arise from this is the main one of the motivations of my research, and hopefully we'll get to some results of this. Okay, so I realize I've spoken for a bit. I want to ask Pretam if there are some questions before I move on to the pedagogy of cavity QED.
Yeah, thank you. We have got a few questions in inbox.
Sure.
So,
okay.
First one, what is the Bose-Einstein condensate?
What is the Bose-Einstein condensate?
And another is, how can we calculate the number of photons in the cavity?
So basically, for what is the Bose-Einstein condensate, the shortest answer is what I was trying to give then. The shortest answer is, if you take a collection of atoms and you cool them to lower and lower temperature, below a certain temperature scale, instead of the atoms distributing themselves over different energies, they all go into the same quantum state. Okay, so this is what is a Bose-Einstein condensate. And as a result, every atom inside this Bose-Einstein condensate has the same quantum wave function. For example, if I have a harmonic oscillator, which is exactly what they did, if you have a harmonic oscillator potential and you put atoms and you cool them, they all go to the ground state of the harmonic oscillator. And you basically get your ground state wave function of a harmonic oscillator that you calculate in quantum mechanics 1. But instead of a single quantum particle, there will be a million quantum particles in that. So that is a Bose-Einstein condensate. That's the shortest description I can give. In terms of counting the number of photons in a cavity, so one very non-destructive way is what I showed with these experiments of Serge Haroche. The second way is if I basically have a cavity and I send in light, and I can put a photodetector outside the cavity. Okay, so then the intensity I observe in the photodetector, since I know the electric field of a single photon of a particular frequency, I can really, from the intensity, work out the number of photons that are inside the cavity, okay, in the steady state. So a cavity is like we will see, it's like a damped harmonic oscillator. And if you drive it, you will send it to some steady state with certain number of photons. And you can find out what is this steady state number of photons by using a photodetector outside the cavity. You don't have to go into the cavity. Okay. So any other questions, or shall I move on?
Okay, how can we calculate the number of photons in the cavity? The next question.
So that's what I was answering just now. Yeah.
Okay.
So I can move on? Okay, great. Yeah. All right. Yeah, great. So then, so after that fairly long introduction, let me go on and describe, as I was saying, this also I described what is the sort of big thing about putting ultracold atoms in a cavity. As I said in the beginning, you can use the cavity light to probe the atomic dynamics. And this is non-destructive, which is interesting because I don't have to touch the atoms. I don't have to go inside the cavity to study what is happening in the cavity. Then the second thing, which I'll hopefully emphasize, is that the cavity has actually a periodic potential due to the electric field. And this leads to coupled atom light dynamics. So the atoms and light talk to each other. And the third thing, which I won't talk about much today, is that the cavity can actually the photons in the cavity can be like force carriers for the atoms, and they can actually induce interactions between the atoms. Okay, so these are also some of the new features that come when you have ultracold atoms in a cavity, and we'll talk about these two features today. And here is a very quick plan of my talk, and we'll see how far I get. Pretam, we should stop at some point. I don't want to keep going on. We'll see how far we get, but I want to begin essentially with a very, very pedagogical primer. Hopefully, I don't know how basic it will be, but let's see, about how to study and discuss ultracold atoms in a cavity. And then if there is some time left, I'll talk about Bloch oscillations in a cavity, which is the theoretical and experimental work that I was part of. And this third part, I'm most certainly not going to get into, that we won't have time, and then I'll conclude. Okay, so let's start with the whole idea of what is cavity QED and the birth of cavity QED as a field. So it started with this effect called the Purcell effect. In order to discuss that, let's begin with a very simple model of an atom. For all that I care about, atoms are just two-level systems. Okay, they are basically two-level systems with energy separation between the excited and the ground state given by omega A. Okay, so they are basically what you would call a qubit. Okay, and physically these are basically an excited atomic orbital of a single electron in an atom, and this is the ground state of, for example, if this is the ground state, you can think of it as a ground state of hydrogen atom. This is the excited state of the hydrogen atom. Okay, one excited state with a particular frequency. And we can we can just pick out one frequency because we are going to predominantly talk to this atom with a laser that is close to this frequency. So the other levels may be ignored. But for now, I'm always going to be in this very toy model of atom. And this is, as we know, for many of our experiments, this toy model works very well. So of course, I want to introduce some matrices or operators corresponding to the atom, which are this EE and GG. This is the sigma Z Pauli matrix, and this is the ladder operator, which destroys an electron in the excited state and brings it to the ground state. With this, I can actually talk about how the atoms interact with electromagnetic fields. The basic idea is that atoms are dipoles. Okay, so there is an electron and it is bound to some positive charge, so it is a dipole. So the dipole moment operator, which is the quantum mechanical version of the classical dipole, the dipole moment operator is just given by the charge times the position operator of the electron. Now I can expand this dipole moment operator in this two-level basis, and I get my dipole moment operator in this manner, where this EDG gives me the transition element or the strength of my dipole moment, which is given by D, and sigma plus sigma dagger is basically EG plus GE, and this small u is the direction in which the dipole moment points. Okay, you do not have terms that are EDE. That is because basically these terms will be zero because of the symmetry of the orbitals of ground state and excited state electrons in some neutral atoms. Okay, so this is the central object. This is the object that allows the atoms to couple to electric fields, which are electric fields of the photons via D dot E interactions, as we will see, dipole electric field interaction, D dot E. Okay, so now, in order to describe this Purcell effect, this is the description of the atom. The second thing I need to talk about is spontaneous emission. You all heard about it in some way or the other in undergrad quantum mechanics. Spontaneous emission is if I put atoms in an excited state, they will not stay there forever. At some point, I do not know when, there will always be an emission of a photon from, and the atom will de-excite from the excited to the ground state, and this happens spontaneously. And to understand that, the fundamental mechanism that gives you spontaneous emission is the fact that even if you do not have any laser light or anything imaging on the atom always sees the electromagnetic fields of the vacuum. Okay, so the vacuum has always some electric fields, and this vacuum's electric field is here denoted by E omega. And basically, one can work out the rate of spontaneous emission by using something called the Fermi-Golden rule, which just tells you, which is just perturbation theory. You take this Hamiltonian that couples D dot E, the atomic dipole, to the electric field modes of the vacuum, and you calculate what is the probability that the atom starts with an excited state and there are no photons, and goes to a state where the atom de-excites and goes to the ground state, and you have one photon somewhere in vacuum. Okay, and then you can calculate this, and this rate is basically enhanced by the quantity that is called the density of states of light, right? So it basically, if you have many states with in principle, if you have a large box of volume V in which you have electromagnetic radiation, the sort that you might have seen in black body radiation calculation, you can calculate the number of modes per unit energy that you have. So at frequency omega A, you can really calculate this very easily, and it goes as omega squared B by pi squared C cube. This is easy to calculate. And this E is the electric field operator of the vacuum, and it has the following form. You can think of the electric field essentially, the electromagnetic field, as basically a bunch of harmonic oscillators. And when you have vacuum, there is harmonic oscillators of every frequency. Okay, so this is basically, in principle, this is the electric field due to a photon of frequency omega. Okay, but you can have all possible frequencies, but to find gamma, you just evaluate this object at the atomic frequency. And this is basically the electric field of a single photon. Okay. With this, you can easily calculate the spontaneous emission rate, and it goes like this, and it depends only on the atomic frequency omega A and the dipole moment d. Okay, and the rest are just fundamental constants. Now, this is spontaneous emission when I put the atom in some very large box of volume V and there is nothing around it. Okay, but now the Purcell effect is basically what happens when you put this atom not in free space, but you put it in between two mirrors, hence in a cavity, right? And now you ask the same question, what is the spontaneous emission rate in this scenario? Okay, now what you have done is you have really changed the boundary conditions of the problem. The electromagnetic field's density of states is not like free space, because I can have standing waves between these mirrors, and it is much more likely when an atom emits a photon that it goes into this standing wave that you can set up between these cavity mirrors. So what happens is you have to replace the density of states by the density of states of electromagnetic field inside a cavity. And that will give you this spontaneous emission rate in the cavity. And the Purcell effect, as we will see in a moment, is just the prediction that the spontaneous emission rate in a cavity is going to be much larger for a very nice cavity as opposed to free space. Okay, that's the enhanced spontaneous emission rate, which is the most sort of basic effect of cavity QED. Okay, so now let's just work out what is the Purcell effect. In order to do that, one has to have a little bit of idea of what is the density of states of a cavity and what is a cavity in some sense. As I said, it is just two mirrors which are separated by some length L, and there is basically a single photon that bounces between these mirrors decays after a time of 1 over kappa. Okay, and this kappa is the damping rate of light inside the cavity. So you can picture this in many ways. You can think of the cavity electromagnetic field as being an oscillator which is damped at rate kappa, and the oscillator has a resonance frequency given by C pi over L, or classically it is just a mirror between which light bounces around and then leaves after 1 over kappa. In either case, a very important quantity that tells you how good a cavity you have is this quality factor, which is the ratio of the time for that a single photon lives in the cavity, 1 over kappa, divided by the time a single cavity takes to do a one full round trip around this cavity. Okay, so that is this L over C pi, and this is 1 over kappa. So when you divide that, you basically get the number of round trips that a single photon makes before it leaves the cavity. Remember that this was the important factor that told us that a single photon interacts very strongly with a single atom in a cavity. And that is controlled by this kappa and basically this frequency, 1 over frequency of the 1 over the resonance frequency of the cavity. So this is a very important quantity, and we'll be interested in high quality factor cavities. Okay. So with that, one can actually write down what is the density of states for electromagnetic field in a cavity, and it turns out that it has this very well-known shape, which from a damped harmonic oscillator, even in classical mechanics, you know that the response of a damped harmonic oscillator is given by 1 over the damping squared plus how far you are away from the resonance, or the detuning squared, right? So then you have this damped cavities density of states, and if you evaluate this damped this cavities density of states at the resonance frequency of the atoms, you can really, from the previous formula, calculate what is the gamma, the spontaneous emission rate inside a cavity, and one immediately sees that this object can be much larger than 1, and this is what is called Purcell enhancement. Okay, so this is basically the 0th sort of thing that was found with cavity QED that led to this field of cavity QED, and people started thinking, oh, if we put atoms in cavities, we will see very different physics. Okay, so that's the Purcell effect. Now, the Purcell effect, in the way that I calculated, it became very clear, hopefully, that I was working with something called the Fermi golden rule, which is assuming that the field and the cavity atom interaction is very weak because it's a perturbation theory. But if you want to discuss situations where the atom light interaction is much stronger, you need a more complete sort of theory. And I want to sort of pedagogically develop that theory a little bit. And this is what I'm going to do. And Purcell effect I'll again illustrate the Purcell effect as the limiting case of a weak interacting version of this theory. So this idea, this basic theoretical formalism begins with the Hamiltonian that describes a single atom inside a cavity. So this is called the Jaynes-Cummings model. This Hamiltonian has 3 parts. The first part basically tells you already know what this is. This is just the free Hamiltonian of the single atom. Then the second part, as I said, is actually the Hamiltonian for the cavity field. As I said, the cavity field is like a harmonic oscillator. This A and A dagger are the ladder operators of a harmonic oscillator. And the resonance frequency of the harmonic oscillator is omega c. Then the third part really comes from the D dot E interaction between the single atom and the single mode of the cavity. So this cavity mode has 2 aspects to it. One is this A, which sets the amplitude of the cavity mode, that sets the amplitude of the electric field, and it has a position dependence, which is very interesting as well. The position dependence is something you can imagine. It's just a standing wave, right? So it's a sine kcz. Kc is just related to omega c. So it is just the wave number corresponding to the resonance frequency. And you have a standing wave potential inside the cavity. Standing wave potential of light inside the cavity. And that is basically coming from this E, okay? So now what you can do is you can combine this dipole moment dot E and combine it into a constant which is called G0, and that is the G0 that will be a frequency that tells me the strength of the interaction between this light field and the atom, okay? So now with this, what we can do is we can ask what sort of physics comes out of this Jaynes-Cummings model. But before we do that, there is an important feature that is missing. This is the Hamiltonian of a single atom interacting with one mode of electromagnetic field, but the electromagnetic field in the cavity, there is no decay. And the atom also, this is just the Hamiltonian, there is no decay or dissipation in this system. So how do you model dissipation in this system? Because you have to add spontaneous emission, which is actually decay. You have to add photons. You have to add the physics of photons leaving the cavity, which is again dissipation or decay. How do you do that? So let's just briefly see how one does that. So the idea is basically that there are 2 sources of dissipation here. One is basically the light field. The atom can emit a photon that leaves the cavity. It doesn't enter into any of the cavity modes, but it goes outside the cavity completely. So this is spontaneous emission, not into the cavity, but outside the cavity. And this is 1 minus the solid angle that the cavity subtends. But essentially, you can think of it as the natural spontaneous emission gamma of the cavity. The second source of dissipation is light that leaves the cavity atoms can emit into the cavity mode, but the cavity modes can emit a photon into the cavity mode, but that photon is not going to remain forever, as we discussed, and will leave after 1 over kappa, and this kappa is the second source of dissipation. So the simplest way to introduce this is basically the fact that you can write, instead of the Schrodinger equation for a quantum system, you can write an effective sort of, you can write what is called a master equation, which is a modified version of the Schrodinger equation, including dissipation. Okay, and there are two components to the modification. The first component is replacing the Hamiltonian by an effective Hamiltonian that includes terms that are not Hermitian, like here, one for dissipation through the cavity and the other for dissipation out from the atom directly into the environment. Then this Schrodinger equation, in addition, this master equation, in addition, has two terms which are called jump terms that describe the actual process where a single photon escapes from the cavity or a single photon escapes from the atom. Okay, and in this picture, this row describes what is called the density matrix or density operator of this atom plus light system. Okay, so this density matrix is a generalization of the Schrodinger wave function, and this allows us to write the state of the system even when you have dissipation. Okay, and this I won't go into a lot of details of, but this allows us to write what are called mixed quantum states, not just pure quantum states that are described by a wave function. Okay, so now with this is the governing equation. As soon as I know the density matrix of my system at initial time, I can plug it into this equation, and this is also an ordinary differential equation and for a matrix. So this is a density matrix. So, and I can calculate what is the density matrix at later times very easily. Okay, and that is what I am going to use to understand the concept of Purcell effect within this mathematical formalism. So the idea with the Purcell effect is that the atom light coupling and the spontaneous emission rate out into non-cavity modes, this is much smaller compared to the cavity damping. Okay, so in this limit, if I look at my ladder of states of my atom plus light, so this is a state that gives me atom in excited state, no photon, atom in the ground state, one photon. Both these states are resonant if the resonance frequency of the atom and the resonance frequency of the cavity are the same. So this is 0 photons in the cavity, this is 1 photon in the cavity. And then this is the complete ground state of my system without any interaction, which is both the atom in the ground state and the 0 photons in the cavity. Okay, now the idea is that I start with an excited state, right, with the atom in the excited state and no photon in the cavity, and now ask the question, what is the probability that I continue to be in the excited state, right? So that probability as a function of time, I can work it out from this master equation, and that is exactly what is going to tell me what is the rate of spontaneous emission. So clearly that probability, this equation predicts, you can plug this in and this is just math, this equation predicts that that probability decays exponentially, and the rate of decay is given by this gamma cavity that we calculated earlier using Fermi-Golden rule. And basically you're able to reproduce the results of the Fermi-Golden rule in a more transparent manner using even more sophisticated theory. Okay. Now, another way of also studying the atoms, as I said, is to take this cavity and you add a driving term to the cavity. So you can actually drive the cavity from the outside with some laser light with some frequency omega p, and then ask what is the transmitted intensity of light as a function of the frequency omega p you use. The interesting thing is that if you're in this limit where the atoms are essentially very weakly coupled to the cavity, the transmission as a function of the driving frequency is perfectly like as though there were no atom inside. There is a small shift here, but that's not important. Basically, this is the Lorentzian shape of the density of states of the cavity that I introduced earlier. And basically, this tells me that if I drive the cavity with laser light that is resonant, I get transmission, but as I go away from resonance, I don't get any transmission. So this is the regime in which you get the Purcell effect, where there is basically very little coupling between the atom and the light, but still the atom preferentially emits into the cavity mode, giving it a much larger spontaneous emission rate. Okay, and so this is the Purcell effect. Okay, so maybe I'll stop here for once again if there are questions. Yeah.
We have a few questions.
Okay.
In comment section. First question: could quantum gravity be tested using ultracold atom?
So can gravity be tested?
Quantum gravity be tested using the ultracold atoms?
So I think so. In some sense, one of the, I don't think I'll get to this in the talk because it's a bit long. But at the end of the day, what you have with ultracold atoms is extremely high precision available to test anything. So essentially, if quantum gravity, for example, predicts that the as it does in some theories, that the Newton's law, which we know, Gm1m2 by r squared, has some corrections at short below 1 millimeter length scale, right? So this is a very famous work of Nimar Kanihamed, where they said that, oh yeah, there should be some corrections to the Newton's law at very small length scales. Now, what we can do is we can design an experiment using quantum gases and ultracold atoms or Bose-Einstein condensates to test or to bound these corrections. And there are experiments to do that. And one way of doing it is, one of the motivations for our work in the early days was also to try and use this as a good motivation to see why we should design this. So the short answer is yes. Now, the one thing that one has to be a little bit careful about is it can only do bounds, or it can only do precision tests at the moment. But there is also another route where people actually try and ask questions if there are real predictions of quantum gravity, which are not just some precision tests, but something physical phenomena that you can do at low energy. So low energy tests of quantum gravity. This does not need ultracold atoms as such, but there are quantum optics experiments where one tries and verify predictions of quantum gravity. So that's a different route, which doesn't require even ultracold atoms. You just need to cool and control quantum systems to a very high degree, where you rule out every other possible source of environmental dissipation. And then if you still see some dissipation or decoherence, then you will say, this should come due to gravity. So that is another route, but that doesn't require ultracold atoms per se. And both routes are interesting, and both routes are followed. These are very, very interesting questions. Yeah.
Thank you. We have another question. So, do quark gluon plasma and ultracold atomic Fermi gases exhibit very similar hydrodynamic flows?
Okay, so this is a very, very deep question. I am not very qualified for this. I can just indicate what I know about it. So this is a very interesting thing that people found. I think maybe even Pretam, who is a nuclear physicist, might know more than me on this. But the idea is that in certain regimes, certain properties, such as you mentioned, the transport properties, seem to exhibit a kind of universality that spans across systems that are extremely different, like quark-gluon plasma or ultracold Fermi gas. Both have fermionic degrees of freedom. That's one ingredient. The second ingredient is that you can tune the interactions in these ultracold Fermi gases so that to a point which is called unitarity, where there is just one length scale in the problem. And in this case, it just is the Fermi momentum. If you can tune the interatomic interactions to that scale, in that regime, the transport properties look like a QGP's transport properties. It has been theoretically shown, and it has also indications of this have been seen experimentally. But experimentally controlling an ultracold Fermi gas at unitarity is a very hard task. So the degree to which it has been achieved, I'm not very familiar with also. But this is actually true, that there is this universality available. Yeah.
Okay, thank you. We have another two questions. So first
Mm-hmm.
one, can we use ultra-cold atoms for neutrino mass measurement?
Mm-hmm.
Another
Okay.
question is, what are the benefits of studying ultra-cold atoms and what are their uses?
Uh-huh. Uh-huh. Okay, so let's see. The first question is neutrino mass. Again, it's a small quantity. If I make a very nice force sensor, I can do it. But I don't know of specific experiments that are attempting it. Though there is some specific experiments that are trying to detect WIMPs, these weakly interacting massive particles, for dark matter candidates using ultracold atoms. But I don't know of neutrino mass experiments for this. The second question: what is the use of studying ultracold atoms? Okay, so there is so there is two ways to answer this question, right? So one way is, as far as just physics is concerned, it's quite rich. So there is, if you're just interested in physics for physics' sake, it is very rich because it is at the intersection of three major fields of physics: atomic physics, um, quantum optics, and many body physics or condensed matter physics. So you will learn all about these three fields. You'll need to understand all these three fields well to work in ultracold atoms. So you will learn a lot, and it will be very interesting. Physics for physics sake. But what are the practical uses? So practically, there are multiple uses now. For example, if you make very good force detectors or very good gravimeters, you can use that as a in people are trying to think of using atomic gases as to check for local gravity, and with this you can use this to search for oil deposits, for example. So this is one field that is used. The second is, of course, these are all building blocks of better and better quantum computers. So these are sort of very tangible long-term benefits of studying this field. I would say these are the two things I can think of. Yeah. Okay.
Okay, thank you.
So how much time do I
So
have, Pretam?
about okay, so 15 minutes because
15 minutes. Okay.
yeah.
So then I think
So
I might
I have
just,
got
okay.
another question. So should
Okay.
I
Yeah,
ask or
sure.
later? We can
Sure, sure,
discuss later.
sure. We can ask. We can ask. Yeah,
Okay,
yeah. No
so
problem.
what are the ways we can use this for the future?
For the future, I guess I kind of commented on it. I don't have many other bright ideas at the moment as to what you could use it for future
Okay.
apart from just cool physics. Okay. All right. Okay, so then let me just change tracks a little bit and move on, and let's see how far we get. But I won't go through the entire pedagogy of ultracold atoms in a cavity, but let me just describe this strong coupling part. So, as I said, the first part we studied about Purcell effect is in the weak coupling limit. Now, if the atom light coupling constant G0 is very strong, something completely interesting, completely different happens. Again, you have these states G0, G1, E0 as your um, eigenstates or ground state and the first excited state when you do not have the interaction. So when this term is 0, this is the ground states. Now, when I add a strong G0, what happens is basically instead of this energy structure, I basically get two new hybridized states. So the new eigenstates are actually just superpositions of G1 and E0, and the energy gap between them is precisely given by 2 times the dipole coupling G0. Okay. And this happens and this 2G0 is significant and large only when this G0 becomes much larger compared to the dissipation rates. And this is marked by this quantity called the cooperativity, which has to be large. Now, very interestingly, if you are in such a regime and you actually run a probe light and look at the transmission, very nicely, instead of a single Lorentzian at the resonance frequency of the cavity, you now get a double Lorentzian peak, one at the resonance frequency plus G0 and one at resonance frequency minus G0, which is precisely indicating this atom photon bound state. So literally these states where there is one photon and atom in ground state, zero photon in the cavity and atom in excited state, a quantum superposition of this state. This is really like a bound state or a molecule state of atom plus light. Okay. And this leads to very different properties of your transmission. And this also means that if you start with an excited state in this regime, E0, it will be a superposition of these plus minus states. As a result, not only will they decay as a function of time, but there will also be these oscillations at the rate of 1 over G0. Okay. So this is the signature of strong coupling between atom and light, and this was seen in beautiful experiments in the group of Gerhard Rempe around the end of 2000. Okay, so this is basically the sort of overall idea of the theory of a single atom inside a cavity. Now we want to not just consider, but in this theory that I was talking about, I was always fixing the atom's position at somewhere in the cavity. So basically, I'm sitting at some given value of z, which is the axis of along the cavity, and I'm looking at the physics. But now I want to consider atoms that move, which will allow me finally to consider a gas of atoms in a cavity. Okay, so now in order to do that, all that I need to do is I need to take the original Hamiltonian, which had these parts, right, and add to it a term that tells me the kinetic energy of the atom's motion along the cavity. Okay. Now, of course, after doing this, I also want to make a small change to the Hamiltonian, where you see that this driving term, laser driving term from the outside, is driving at some frequency omega p, which is the pumping lasers field. And there are a bunch of different frequencies around, but the absolute values of these frequencies are not important. What is important is the relative values of the frequencies. One relative value, which is called the atomic detuning, is basically the pump frequency minus the atom's frequency, and the other one tells you the pump frequency minus the resonance frequency of the cavity. So in order to make these the central objects, I can do a rotating frame transformation to this Hamiltonian, and it becomes into this form. Okay, the details of this are not super important, but once I have this, again, I can describe the same physics, but now the atomic motion is included. Okay, now I had some slides on what sort of interesting physics can come out of this atom's motion, but I'm going to quickly skip ahead. But before I do that, I want to talk about the limit in which I'm going to always consider this system, which is this detuning between the atom and the photon is going to be much larger than all the frequencies in this system. In this limit, I can do something very nice, which is I can basically now forget about the internal level of my system. So the atom's excited and ground state internal level, I can eliminate it in what is called an adiabatic elimination, where I basically do not care about whether the atom is in the excited or ground state, or since I'm driving the system with light frequency that is far detuned from the atom's resonance frequency, the atoms are rarely excited. So the atoms are going to be mostly in the ground state and basically a little bit excited. And I can use that to essentially eliminate the internal degrees of freedom of the atom, which is this sigma 3, sigma, these operators completely from this equation. And this is this adiabatic elimination. And in this limit, I can write down my Hamiltonian of my atom light interaction as basically in this very nice form, which talks just about the external or position degree of freedom of the atom. So a single atom in a cavity in this dispersive limit as just these terms. This term is the kinetic energy of the atom. This term is the driving of the cavity. This is the cavity's resonance frequency, detuned delta C. This is basically the key term that tells us that the cavity essentially provides a periodic potential for the atom. So if you think of this from the atom's point of view, this is just a sine squared kcz. So if I forget for a moment the number of photons in the cavity, A dagger A, this is really just a periodic potential for the atoms in the cavity. The strength of the periodic potential is controlled by the number of photons in the cavity, which is given by A dagger A. So this is the setting of a single atom moving inside a cavity. Okay, so now if I quickly forward, and of course, sorry, one more thing to mention is if I want the atom and light inside the cavity to interact strongly, I would want this quantity, this G0 squared by delta A. This should be much larger than the dissipation. Okay, and this, if it happens for a single atom, this is called the single atom strong coupling, but in the dispersive limit. But what I can do, let me skip these slides. But what I can do instead is I can actually instead of a single atom, I can put many atoms, right? And as a result, I can actually enhance this U0's value by adding many atoms. That is one way to do it. Now, the main sort of thing I want to talk about in the last 5 minutes is to consider a situation where instead of adding many atoms one by one, what happens if I actually add a Bose-Einstein condensate into the cavity mode? So in this limit, basically instead of a single atom, I have n, very large number n of atoms, all of them in a given wave function psi of zt. Okay, so instead of a single classical atom moving inside the cavity, now I actually have a quantum gas or essentially a matter wave moving inside the cavity. And in this limit, the atomic dynamics is going to be given by a kind of Schrodinger equation, right? So this is the Schrodinger equation, and it has the kinetic energy term, and it has a potential energy term that is proportional to the intracavity potential, which is this sine squared kz that I talked about. And it also has the strength of this potential is controlled by the number of photons in the cavity, which in this classical cavity field limit is just the square of the electric field amplitude alpha. Moreover, this electric field amplitude has dynamics as a function of time. All of this is coming from this original Hamiltonian we had with the interaction between the atom and light. And the dynamics of this cavity field is precisely controlled by the presence of the atoms. Instead of looking at each atom, now we have actually an integral over the density of the Bose-Einstein condensate. And as the atoms move inside the cavity or do some dynamics, this psi of zt changes. And as it changes, basically the detuning of this cavity mode from resonance changes, and that changes the number of photons in the cavity. And that is the main idea behind this Bloch oscillations I just want to talk about in the last 1 minute. Okay, so this is describing the dynamics of a Bose-Einstein condensate in a cavity. Okay, so now if I can finish with actually a cartoon slide of the central work we did. For that, I just want to quickly talk about Bloch oscillations, and then I can talk about our work. Okay, so what are Bloch oscillations? This is very basic quantum mechanics phenomena. So when you have a particle in a periodic potential, okay, this is representing a periodic potential in one dimension, and then you put a particle and you add to this periodic potential a constant force. So V of z is equal to minus f times z, and you add this tilted potential, right? So this tilts this periodic potential. If you had a classical particle, what you would expect is that the atoms are just going to go down this potential and leave the potential, right? So it would just roll down this hill slowly. On the other hand, if I had like a Bose-Einstein condensate or a matter wave or a quantum mechanical system, instead of doing that, they oscillate at, they go up and down this lattice and oscillate at a frequency that is called the Bloch frequency, and it is given by the force you apply times the periodicity divided by h bar. Since you can really very well control the periodicity of these optical lattices or optical potentials, measuring the Bloch frequency will give you an very precise measurement of the force. Okay, so now the idea, as some of the questions asked, was if you can measure this force very well, you can do very interesting stuff. So you can measure hard to measure forces like Casimir-Polder, measure capital G precisely, because this is one of the least well-known fundamental constants. This is the gravitational constant, and you can measure gravity at short distances. This was the idea that I was mentioning a little while ago. So for these reasons, finding a very precise way to measure Bloch frequency is very interesting. And our central idea in our work that I wanted to just tell you is to measure this Bloch oscillations. I'm not going to go into the details of Bloch oscillations, but the central idea in our work was to use, instead of putting a quantum particle in a light-induced potential in free space and measuring the Bloch frequency, we wanted to consider, remember that the cavity produces an periodic potential. We wanted to put atoms inside this cavity and use the cavity to study and measure the Bloch oscillation frequency of the atoms. Why do you want to do this? The first reason is you can actually let the atoms oscillate, and as they oscillate, by looking at the light that escapes from the cavity, one can really study the Bloch or calculate the Bloch, measure the Bloch frequency. The second interesting thing I've already said is there is an interaction between the light and the atoms that is interesting. So let me very briefly describe the physics of this proposal and one slide of the experiment, and I'll conclude. So the idea is, as I said before, you have a cavity and you put a Bose-Einstein condensate inside the cavity. The cavity produces a periodic potential of the light, right? This is basically the standing wave inside the cavity, and the Bose-Einstein condensate is moving inside this potential because I'm applying, for example, a linear force. This could be just due to local gravity. So now the interesting thing is we had this coupled equation for the amplitude of the intracavity light field alpha and the density distribution for the atoms. So what happens is basically as the atoms Bloch oscillate, the intensity of the light field inside the cavity changes at the same frequency as the Bloch oscillation frequency. And this precisely is being shown here. This is the amount of light inside the cavity, and that light eventually escapes from the cavity, and you can put a photodetector here and you will see intensity oscillations, and the period of this intensity oscillation is precisely given by the Bloch period, and from which you can calculate the Bloch frequency. Okay, so this is the entire idea. And as I was saying very briefly, let me just show this, the theory. Sorry, it's just taking a little bit of time. Yeah. So the theory aspect of this is that I have now this Schrodinger equation now where there is a periodic potential and the force, but the periodic potential's amplitude is controlled by the number of photons in the cavity, but the photons dynamics is in turn controlled by the cavity, by the atomic density distribution in the cavity. So this coupled dynamics is what gives rise to the possibility of studying the Bloch frequency by just looking at the intensity of the light that escapes the cavity. Okay, so this is the one main application of ultracold atoms in cavity that I have worked on, and this was a theoretical proposal which we looked at during my PhD. But eventually, I just wanted to show the last slide, which shows that I could make. I was also fortunate to be part of an experiment where they actually managed to implement our idea, and one could actually see this very nice behavior. So this is an experimental plot where you basically have in this blue curve is actually the light field inside the cavity, and that oscillates at the Bloch period. And this and to verify that it is really Bloch oscillations that is causing this, one can also additionally study the atoms inside the cavity. So these red lines are the momentum, average momentum of the atoms, which is also oscillating due to the Bloch oscillations, and these green lines are giving you the position of the center of mass of the atoms. You can see them oscillating very nicely. Okay, and from this one can read out the periodicity, and this experiment was more proof of principle, but there are people who are still trying to see if one can use this as a precision sensor for some interesting force sensing and so on. Okay, so that's in the future. That's so far. So at the moment, I just want to conclude by flashing my conclusions. So I hope at least I was able to give you a flavor of the fact that ultracold atoms in a cavity, this is a very interesting system, and it's a versatile light matter interface. The second thing is, this was briefly, I was talking about Bloch oscillations can be non-destructively measured by looking at the cavity light that escapes. And this is, again, I couldn't get to it, and I'm interested now in more interesting aspects of this cavity physics, many body physics, and so on. And one answer I wanted to give to a question that asked, why should we study ultracold atoms? It just struck me now. This is actually one of the very, very, very few fields in physics where one can propose an experiment during their PhD, and it can be tested 3 years later, like it happened in my case. And this is routine because this is not a earth-shattering proposal that I made, but it is very interesting and a simple proposal, but even that can be tested very quickly. So this is something I cannot emphasize how important this is in physics, which is in theoretical physics, where you do theoretical physics that can be tested in an experimental lab as soon as possible, because that will enrich both your theory and it will provide you with more interesting questions that you can study, right? So that's one big thing. And this is my collaborators who helped me do all of this work. And finally, before I leave, I just wanted to leave you with a few snapshots of where I am at. This is IIT Gandhinagar. I'm not sure if there was someone else from IIT Gandhinagar that spoke before that showed some pictures. So this is where we are in Gujarat, on the banks of the Sabarmati River. And these are pictures of campus. This is the main academic building. This is also the academic building. These are all the academic building snapshots. And this is the very nice hostels that we have for students. And I wanted to just flash this advertisement that we continue to really look for international students in our PhD program and MSc and MTech programs. Okay. And also we have all sorts of programs on for especially from graduate level. You can do a full degree at IIT Gandhinagar. And if you're an undergrad, you can also try to spend a semester abroad and come and visit IIT Gandhinagar. You can write to these basically this email ID and look at this website for more information. I especially encourage students from Bangladesh because you are part of the SARC and you can get special scholarships while you're doing PhDs as well. So this is a very good opportunity, and I hope at least some of you consider IIT Gandhinagar to do your PhD. Thank you so much.
Yeah, thank you for sharing this information with us. I think it will help our student. So we have got few questions. In this section also, if you allow, we can start. The first one, it is said cold atom might help understand superconductors. So how?
Okay, so this ultimately is got to do with the first set of pictures I showed about quantum simulation. A very good example of how it might happen is the following. So if you remember that I showed you this picture of an superfluid Mott insulator transition where I had ultracold atoms placed into this periodic potentials of light. Okay, so now it is known that the basic Hamiltonian of this system, I showed a case where it was bosons in an optical lattice. If I took fermions and put them in such an optical lattice, this realizes a Hamiltonian that's called the Fermi-Hubbard Hamiltonian. It is known that it is this Hamiltonian, especially in 2 dimensions, that is responsible for the phenomena that give rise to high TC superconductivity. So high transition temperature superconductivity, which is a completely unsolved problem. You can actually simulate that high TC superconductivity using fermionic atoms in 2-dimensional optical lattices. But of course, this is the scheme. And if you can do this, you have the answer to high TC. But doing this requires taking fermions in optical lattices, lowering their temperatures to scales comparable or smaller than the Fermi temperature. And it's a big challenge, and it's a big sort of goal in the field. We are making slow but steady progress towards it. But eventually, I would say within the next few years, we will see a very good understanding of high TC superconductivity emerge from such ultracold atom experiments. The idea is precisely the Fermi-Hubbard model that I showed before. Yeah.
Okay, thank you. Now we have another question. So, what about cold atom for quantum computers or technology? How can it be used?
Right. Okay. So there are 2 broad ways in which one can think of cold atoms and quantum computing. The first way I did not talk about at all in this talk, which is you can actually trap charged particles in. So this is called ions. So you take an atom, you kick off one of the electrons, and you make an ion, and you can trap these charged particles in electromagnetic traps. So these are called the trapped ion systems. And then you can trap many such ions, and you can build a quantum computer out of these ion systems. So this trapped ion quantum computing is one very promising big direction for small quantum computers. Of course, making this into a full-scale quantum computer is hard, but you can do up to like 20-30 ions very easily nowadays, and currently there are experiments in Innsbruck and in US also on this. The second sort of more interesting direction that has developed is with these neutral atoms, and in fact with these very cool atoms that Serge Haroche used, the so-called Rydberg atoms. So now there is technology where you can trap up to almost 100 of such Rydberg ions in an array. Okay. And these Rydberg ion arrays, Rydberg atom arrays, these are neutral atoms, but with very large dipole moment. This provides a very, very interesting setup for quantum computing. Again, you can do very interesting quantum computing tasks on this, and this is an extremely fast developing field. So these are, I would say, two of the most promising routes for quantum computing in the sense of a general purpose quantum computer. What do I mean by that? You give me a algorithm or a particular quantum computing task, I will do it like I will use the quantum system as a processor. For such things, you need a general purpose quantum computer. But I would argue that this quantum simulator is also a kind of quantum computer. So it is what is called an analog quantum computer, where you give me a Hamiltonian and I can do an experiment and tell you the ground state. Instead of doing a computation on a computer, I will use my experimental quantum system to spit out the ground state of a complicated quantum system. So that analog quantum computation is the central idea of quantum simulation. But you can do also this digital quantum computation with ultracold atoms. These are the two things I said. Yeah.
Thank you. This may be the last question. So what about NASA's cold atom lab in International Space Station? Comparing cold atom lab from space and from Earth, is there more advantage in having it to space than in Earth?
Sure. I mean, so there are. So, for example, one thing that you have, one of the big challenges when you build one of these ultra cold atoms labs is that whenever you're on Earth, you're in some basement far away from as much as possible vibrations and noise these are very, very sensitive systems. So it is, of course, if it's advantageous to go to more and more pristine environments. So that is one advantage of space. The second advantage is basically that there is no local gravity. So now, in some sense, it's not a big shift, because most of this physics that we do, we don't add the gravity component to it because you never saw any gravity in whatever I did, because I kind of imagine that there will be some addition that is not so important. But now it is interesting to understand what happens in microgravity to all of these phenomena. And some phenomena, especially if you want the more subtle, let's say, quantum gravity induced phenomena or something like that, maybe it's much easier to study in space. So these would be the main advantages as far as I can think of, but there could be more that I may not know of.
Yeah, thank you for your wonderful presentation and discussion session. As the main aim of our program is to motivate our students, I think by your excellent lecture, some of our students should be motivated. So I have got last question. So if you allow, I can just read it out.
Sure.
Okay, so how can ultra-cold atoms be used in quantum simulation or many-body quantum system?
So that is exactly this example of this superfluid Mott insulator I said. So the idea is very simple. The idea is I have a toolbox, which is I have atoms that I can control very well, and I can shape these optical lattices into different potentials. So now, and these atoms can interact between themselves, and I can tune the interactions between the atoms as well. So what I have in essence is I can essentially experimentally create any many-body Hamiltonian that you have in mind using ultracold atoms. So not only can I create that, then I can load my atoms into this Hamiltonian, or like I can realize this Hamiltonian with my atoms, and I can look at the ground state properties of this. So this is exactly like actually taking a computer and using Python or something and putting in Hamiltonian and saying, find the eigenvalues. This I can do in a lab. That is literally what this quantum simulation is about.
Okay, thank you. So thanks for giving us this opportunity to arrange such an important webinar, and hopefully in the near future we can arrange, because you haven't finished, because there's something left, so we can arrange another webinar for that.
Thanks,
So
Pretam,
bye.
and
Yeah, it's my pleasure.
thank you. Thanks for your time.